The chemical characteristics of an element are determined by the number and arrangement of electrons around the atom's nucleus. These are described by quantum mechanics. And if you're willing to wait for about 2 or 3 more years, I'll be very happy to tell you all about that in my quantum chemistry class. But in the meantime, let's talk about one fundamental principle of quantum mechanics and also a ukulele. So in order to simplify some of the math and give a better physical model of infrared light, Max Planck introduced the world to an idea that energy levels could be quantized or discrete, according to energy equals n, or an integer value, times some constant, which we now call Planck's constant, and is equal to 6.626 times 10 to the negative 34 joule seconds, multiplied by the frequency, often shown as a nu. It looks like a small v. What he didn't know, and what Einstein later showed, is that it's not just a mathematical trick or convenience, but energy really is quantized into discrete levels and not one continuous band. But what does that have to do with electrons in an atom? And what does any of it have to do with my ukulele? Well, if I pluck one of the strings, we hear a specific frequency. And that frequency is determined by how tightly the string is strung, and also by the length of the string. So you tune the frequency of a ukulele string by adjusting the tension on the string, or the force that's holding that string tight. The force that holds an electron tight to a nucleus is the electrostatic charge on the nucleus. And since that goes up according to the number of protons, and we can only climb the number of protons in integer values, we can't have half a proton, then the energy is also rising by integer values. And this is controlled by the principal quantum number, the first quantum number that we're going to introduce, also called n. The length of the string also determines its frequency, because frequency and wavelength are proportional to each other. So any wavelength that doesn't multiply exactly into that length of the string ends up interfering destructively with itself and canceling itself out. Only resonant frequencies, or the frequencies whose wavelength does fit exactly inside the length of the string, can stick around long enough for us to hear. Electrons are a bit like that too, but instead of vibrations on a one-dimensional string, stable electrons are described by a wave function that fits into three-dimensional orbitals. These orbitals determine where the electrons can be found in space, and they're controlled by two numbers, the angular momentum number L and the magnetic number M. In chemistry, we refer to the orbitals by a letter name instead of by its angular momentum number. So instead of 0, we would call it the s orbital, 1 becomes the p orbitals, 2 is the d orbitals, 3 is the f orbitals. 4 would be the g orbitals, but so far we don't need those to describe any known element. Electrons also have a property that's uniquely quantum and can't have any comparison in the classical mechanics. That's spin. Spin can either be plus or minus 1/2, or what we'll often call spin up and spin down. When we're filling electrons around a nucleus to build an atom, no two of those electrons in the atomic system can have the same set of quantum numbers. So no two can have the same energy level, end orbital, and orientation of that orbital, or what we get out of the magnetic quantum number, and spin. So each of the orbitals inside of the energy level can have two electrons, one spin up and one spin down. And like everything else in nature, we start filling the electrons from the lowest energy value, or the lowest number, first. So principal quantum number 1 and orbital number 0, or the s orbital. And then we start building our way up.